Welcome to Chapter and Verse, the show that takes a stack of sources and extracts the most important nuggets of knowledge or insight, giving you a shortcut to being well-informed. Today, we're embarking on a deep dive into some of the biggest questions humanity has ever grappled with. What is time? What is reality? And can we truly predict the future? These are pretty mind-bending concepts, and our mission today is to cut through the complexity and guide you straight to the fascinating core of these ideas.
And for this particular deep dive, our source material is really something else. It's Stephen Hawking's groundbreaking book, The Universe in a Nutshell. It's a work he himself described as having a kind of tree structure,
Yeah.
designed to make these incredibly complex ideas more accessible than his earlier work, which was maybe more linear. He wanted people to be able to jump around, explore different branches, and still get the fundamental concepts.
That's right. So our goal is to unpack the most important insights from this incredible source. We'll guide you through Hawking's core ideas without getting too lost in the technical weeds. Think of it as a personalized tour through the cosmos, maybe with all the surprising facts and just enough humor to keep you hooked. Let's dive in. Okay, let's unpack this. Our journey begins, just like Hawking's book does, with the twin pillars of modern physics, relativity and quantum theory. And where else to start but with the scientific rock star himself, Albert Einstein. What's often forgotten, though, is that Einstein wasn't some, child prodigy right from the start. He was actually a young man from a struggling family, working a junior post at a Swiss patent office in Bern. That's when he wrote his 3 revolutionary papers in 1905. These weren't just scientific papers. They launched conceptual revolutions, fundamentally changing how we understand time, space, and reality itself.
Yeah, and what's fascinating is how these revolutions started by tackling a really big puzzle from the 19th century. Scientists back then believed space was filled with this continuous medium called the ether. They thought light waves needed something to travel through, like sound waves need air, and they figured light would travel at a fixed speed through this ether, so its speed relative to us would change depending on how we were moving. But then came the crucial Michelson-Morley experiment in 1887 in Cleveland, Ohio. And it delivered this really shocking blow. It found no difference in the speed of light no matter how the Earth was moving. Light just always traveled at the same speed, didn't matter how you were moving or where.
Right. And Einstein's radical step, just a few years later, was to basically just ditch the ether concept completely. He proposed that the speed of light is constant for all observers, no matter their motion. And the really mind-bending consequence of this, we had to abandon the idea of a universal time. That means everyone has their own personal time.
Yeah.
And this isn't just theory, right? It's been tested, confirmed rigorously.
Oh, absolutely. The famous twin paradox prediction, well, it was experimentally validated. They flew 2 extremely accurate clocks in opposite directions around the world. And when they brought them back together, the clock that flew eastward had recorded slightly less time. It's a tiny, tiny fraction of a second, but it proves it. Time is personal relative to your motion. Hawking even joked that any time you gain flying east would be more than canceled by eating airline meals.
Okay, so personal time, a constant speed of light, and then, of course, the most famous equation in physics. E must equal. Everyone knows it, but what's the deep fundamental insight it offers about the universe?
Well, the real brilliance of EMC Trod isn't just about, unlocking destructive power. It's the fundamental revelation that mass is concentrated energy. And energy can become mass. They're interchangeable. That kind of fluidity was just unimaginable before. It implies that as you accelerate something, its mass actually increases, making it harder to accelerate further. So reaching the speed of light would take infinite energy, which is why you can't. The profound implication of this equivalence was starkly realized in 1939. Scientists, worried about the looming war, persuaded Einstein, who was a pacifist, to urge President Roosevelt to start nuclear research. That led to the Manhattan Project and the atomic bombs. But Hawking makes a really crucial point here. Blaming Einstein for the atom bomb is like blaming Newton for plane crashes because he discovered gravity. Einstein wasn't involved in the project and was horrified by the bomb's use.
Right. So building on this revolutionary idea of personal time and the constant speed of light, Einstein then tackled gravity. That was his general theory of relativity. Newton's gravity implied instantaneous action across the universe, didn't it? But special relativity said nothing can go faster than light. How did Einstein fix that contradiction?
Yeah, that was the big question Einstein chewed on in Prague around 1911. He had this profound brainwave. The equivalence principle. Imagine being in a closed box, like an elevator. You literally cannot tell if you're at rest in Earth's gravity or being accelerated by a rocket in deep space. Hawking playfully notes this was pre-Star Trek, so it was elevators, not spaceships, that sparked these thoughts. This led him to the key idea. Mass and energy don't just attract things, they warp space-time itself. Objects try to move in straight lines through this warped space-time, but because space-time is curved, their paths look bent as if by gravity.
The classic analogy is the rubber sheet, right?
Yeah.
With a heavy ball making a dent and smaller balls rolling around it like planets.
Uh.
But you often hear Hawking say it's incomplete. Why? Because it only shows space being curved, not time.
Exactly. In relativity, space and time are woven together into this four-dimensional fabric, space-time. You can't curve space without affecting time, and vice versa. So time literally has a shape, a geometry. It's determined by the mass and energy within it. Einstein, with help from the mathematician Marcel Grossmann, finally nailed down the equations for this in 1915.
And the confirmation was just spectacular. In 1919, that British expedition observed starlight bending around the sun during an eclipse, exactly as Einstein's theory predicted. Hawking calls this the greatest change in our perception of the universe, since Euclid wrote his Elements of Geometry around 300 BC. That's huge. But then Einstein made what he later called his greatest mistake, didn't he?
He did. His original equations didn't allow for a static universe, which is what he and pretty much everyone else believed in at the time. So he added this cosmological constant, a kind of fudge factor, like an anti-gravity, to balance things out and keep the universe static. But then in the 1920s, Edwin Hubble's observation showed the universe was definitely expanding, so the constant wasn't needed. Einstein famously called it his greatest mistake. But here's the really wild twist. Modern observations actually suggest a small cosmological constant does exist. It seems to be accelerating the universe's expansion today.
Wow, so maybe not such a mistake after all. This also means general relativity predicts a beginning to time, what we call the Big Bang, and potentially an end to time, inside black holes formed from collapsing massive stars. But Einstein himself was apparently uncomfortable with these ideas. He felt they showed his theory breaking down.
He was. He thought his model wouldn't hold up at such extreme densities. However, Stephen Penrose and Hawking, in their 1968 paper, proved that classical general relativity must predict singularities. These are points of infinite density where the theory itself breaks down, meaning the universe did begin in a Big Bang, and time ends inside black holes, at least classically. They apparently won $300 for that paper, which, seems like a bargain for proving the universe had a beginning. But this very breakdown of classical physics at these extremes forces us towards the other great revolution of the 20th century, the totally weird, counterintuitive world of quantum theory.
Ah, the quantum realm. Okay, this is where things get really, really strange. It started with Max Planck in 1900, discovering that light doesn't come in continuous waves but in discrete packets, or quanta. And Einstein, again in 1905, used this idea to explain the photoelectric effect. That's the basis of modern light detectors, right? And it actually won him his Nobel Prize, not relativity.
Exactly. Then came quantum mechanics proper, with Heisenberg, Dirac, Schrödinger. And suddenly, particles didn't have definite positions and definite speeds at the same time. The more accurately you know one, the less accurately you can possibly know the other. That's the uncertainty principle. Einstein famously hated this inherent randomness. He said, God does not play dice.
But Hawking's view, as he puts it, is that God is quite a gambler. And despite Einstein's discomfort, these quantum laws, the ones governing the tiny subatomic world, are the foundation of basically all our modern technology. They've transformed everything in the last 50 years or so. So there's this fundamental tension, isn't there, between relativity's smooth, curved space-time and quantum theory's fuzzy, probabilistic, discrete world. Okay, so we've laid the groundwork with relativity and quantum theory. We've seen how Einstein totally reshaped our understanding of space and time into this single fabric. So the next big question is, what is time itself, really? How does it behave when you look at it through this new relativistic lens? Is it like that old hymn, an ever-rolling stream, or more like Newton thought, a fixed railroad track, infinite, separate from space?
Well, Newton's model definitely saw time as this infinite, independent line, an absolute background, which led to philosophical headaches like Kant's antinomy of pure reason. If the universe existed forever, why hasn't everything that could possibly happen already happened? But Einstein's general relativity from 1915 just completely rewrote the rules. And Hawking takes what he calls a positivist approach here. A scientific theory is basically a mathematical model. It has to describe observations and make testable predictions. If it fails, you ditch it or change it. And from this viewpoint, time isn't some absolute background stage.
Right, and Einstein's model, which we've refined since then, it truly combines time with the three dimensions of space, creates space-time. And the crucial bit is that mass and energy warp this space-time, which means time itself literally has a shape.
That's the profound shift. Time and space aren't independent actors in general relativity. They're defined by measurements within the universe. So it's perfectly possible for time to have a beginning or an end. It actually makes no sense to ask what happened before the beginning or after the end. The Penrose and Hawking singularity theorems we mentioned prove that classical general relativity predicts a beginning, the Big Bang, and an end inside black holes.
You mentioned the Big Bang is a singularity, a point of infinite density, where classical general relativity just breaks down. That's a huge challenge for our understanding, isn't it?
Exactly. Classical theory just can't cope with singularities, and quantum theory brings its own set of challenges when you apply it to the fabric of reality itself. What's really wild here is that even empty space isn't really empty. It's fizzing with quantum fluctuations, virtual particles popping into existence and vanishing again constantly. If you just add up their energy naively, you get an infinite energy density, which gravitationally should have crushed the universe into a single point instantly.
But obviously that didn't happen. And incredibly, we actually have experimental proof for these vacuum fluctuations, the Casimir effect, where two parallel metal plates close together actually get pushed towards each other slightly because there are fewer virtual particle waves possible between them than outside.
Precisely. The energy difference creates a tiny but measurable force. It proves this vacuum energy is real and has gravitational effects. So this raises a big question. How does the universe deal with these potential infinities from quantum fluctuations? One idea, though it feels a bit tacked on, what scientists call ad hoc, is to have a perfectly tuned negative cosmological constant to cancel it out. But in the 1970s, a much more elegant idea emerged, a new kind of symmetry called supersymmetry.
Supersymmetry. Sounds neat.
Yeah.
So the idea is that every particle we know has a kind of mirror particle, a superpartner that balances out its energy. How does that cancel the infinities?
That's the core idea. Supersymmetry proposes that every particle has a superpartner with a spin that differs by half a unit. Crucially, the positive ground state energies of particles called bosons force carriers, like photons, get exactly canceled out by the negative ground state energies of fermions, matter particles like electrons and quarks. It's a beautiful mathematical cancellation. It gets rid of the biggest infinities very neatly. This led to theories called supergravity. Then, around 1985, the focus shifted to supersymmetric string theory, which initially claimed to be the theory of everything because it seemed completely free of these infinities. Strings are these tiny, vibrating, one-dimensional things, and their different vibrations look like different fundamental particles.
So strings have this special property that perfectly balances everything out, canceling infinities. Okay, but then the story changed again, right? Strings weren't the full picture.
Not quite. It turned out strings are just one type of a more general object called the p-brane. Think of it like this. A point is 0 brane, a string is a 1 brane, a membrane is a 2 brane, and so on. P just stands for the number of dimensions. This led to p-brane democracy, the idea that all these branes might be equally fundamental. And these p-branes exist naturally as solutions within supergravity theories, which usually live in 10 or 11 dimensions. We only see 3 spatial dimensions plus time because the extra 6 or 7 are thought to be curled up incredibly tiny, far too small for us to notice directly.
And Hawking, being a positivist, would say asking, do extra dimensions really exist, is kind of meaningless, right? The only question is whether models with them describe the universe we observe. What's really compelling about these extra dimensions and this unifying framework called M-theory that connects all the string theories and supergravity is this idea of a web of dualities. What's that about?
Yeah, the dualities are fascinating. They show that seemingly completely different theories, maybe describing particles at different energy scales or even in different numbers of dimensions, are actually just different perspectives on the same underlying M theory. It's like having different maps of the same country. One shows roads, one shows terrain, but they're describing the same place. It strongly suggests we're heading towards a single, unified theory. Hawking jokes that ignoring these dualities would be like believing God put fossils in rocks just to fool Darwin.
Okay. And to give time a shape in this quantum world, Hawking introduces imaginary time. Sounds like sci-fi, but it's a well-defined mathematical trick, like adding a fourth spatial dimension, mathematically speaking, that's at right angles to real time.
Exactly. It's a mathematical tool. But using it leads to a really audacious, potentially game-changing idea, the no-boundary proposal developed by Jim Hartle and Hawking. This proposes that the history of the universe, when described using imaginary time, is a closed surface. Think of the surface of the Earth. It's finite, but it has no edge, no boundary. There's no point south of the South Pole. So in this picture, the universe has no beginning in the sense of an edge where the laws of physics break down. It means the universe could be completely self-contained. It doesn't need anything outside itself to kick it off, and the laws of physics are the same everywhere, even at the beginning.
It's, well, wow, self-contained, no edge. And imaginary time also connects to the idea that space-time itself can have a temperature, which is how Hawking discovered black holes radiate. And it even hints at holography, the idea that all the information in a volume of space might actually be encoded on its boundary, like a 3D image stored on a 2D hologram. So maybe we're living on a three-brain. It's just the boundary of some higher dimensional space. This radical shift in thinking about the universe's origins naturally leads us to another ancient human obsession, trying to predict the future. But first, let's talk about the universe in a nutshell, itself the title. Hawking opens with that Hamlet quote, "I could be bounded in a nutshell and count myself a king of infinite space." It's a great metaphor for our ability to grasp the cosmos. But how do we even know the universe isn't infinite and eternal?
Well, we can start with something called Olber's paradox. It's a simple question. If the universe was infinite, infinitely old, and filled with stars everywhere, why is the night sky dark? Every single line of sight should eventually hit a star, making the whole sky blaze as brightly as the sun's surface. The fact that it's dark tells us the universe can't have existed forever looking the way it does now. Something must have happened a finite time ago.
And that something connects to the discovery of the expanding universe, right?
Mm-hmm.
Edwin Hubble, back in the 1920s, he found galaxies are flying away from us, and the farther away they are, the faster they're receding. You run the clock backward, everything must have been much closer together in the past, leading back to some incredibly dense state about 10 to 15 billion years ago.
Exactly. And as we discussed, Penrose and Hawking showed that Einstein's general relativity implies the universe and time itself must have begun in this massive explosion, the Big Bang. For Hawking, being a scientist means you have to try and understand that beginning using science. You can't just say the laws of physics were suspended back then because, as he argues, a law isn't really a law if it only holds sometimes.
So we're back at the Big Bang, that point of infinite density where general relativity throws up its hands. But this is also where quantum theory, with its built-in randomness, becomes absolutely crucial. Einstein hated the idea that God does not play dice. But Hawking says God is quite a gambler. How does that gambling play out at the universe's birth?
He uses a casino analogy. Today, the universe is huge. It's like there are countless rolls of the dice happening all the time, so things average out very predictably. That's why classical laws work so well on large scales. But near the Big Bang, the universe was incredibly tiny. There were only a small number of rolls, relatively speaking. So the uncertainty principle, the inherent fuzziness of quantum mechanics, dominated everything. And this leads to a really radical concept. The universe doesn't have just one single unique history.
Okay, here's where it gets really wild. Richard Feynman's idea of multiple histories.
Yeah.
The universe doesn't just take one path from the Big Bang to now. It simultaneously explores every possible history. Each history has its own probability. Even as Hawking puts it, a history where Belize won every single gold medal at the Olympics, though the probability for that one is vanishingly small. And you're saying this is now considered science fact?
Within the framework of quantum mechanics, yes. It's called the sum over histories approach, and it's fundamental. And this ties back neatly to the Hartle-Hawking no-boundary proposal we just talked about. In imaginary time, these histories are represented as closed surfaces, like the surface of the Earth. There's no starting edge or boundary needed, which reinforces the idea that the universe could be entirely self-contained, needing nothing outside itself to get started.
Okay, and this brings us to another really crucial, sometimes controversial idea, the anthropic principle. The basic idea is that the mere fact that we exist as intelligent observers capable of asking questions about the universe places constraints on the kind of universe we could possibly find ourselves in. It's not just saying things are the way they are because we're here. It seems deeper than that, like our existence filters reality.
It's a powerful constraint. It suggests a deep connection between the observer and the observed. A really compelling example is the number of spatial dimensions we experience. Why? 3. Well, Hawking points out that if there are only 2 spatial dimensions, complex life like us couldn't exist. An organism with a digestive tract would literally be split in 2. And if there were 4 or more spatial dimensions, planetary orbits wouldn't be stable, and even atoms might not hold together properly because the electrical force law changes. So only 3 large spatial dimensions seem to allow for the kind of stability needed for complex structures and eventually intelligent life to evolve. Our existence basically selects for a 3-dimensional universe from all the possibilities.
Then there's inflation, this idea of a period of incredibly rapid, accelerating expansion very early in the universe's history. You said inflation is very beneficial because it smooths everything out, making the universe look remarkably uniform on large scales today. And Hawking mentions the total energy is 0. Idea positive energy and matter perfectly balanced by negative gravitational potential energy. He jokes, if only the banking world were so simple.
Exactly. Inflation solves several cosmological puzzles. While a perfectly smooth, round, imaginary time history corresponds to a universe that inflates forever, probably too smooth, for structures like galaxies to form slightly flattened sphere histories are much more likely. And these slightly imperfect histories correspond to inflation in real time that eventually slows down, allowing gravity to pull matter together to form stars and galaxies, and ultimately us. The amount of inflation needed is just staggering. A billion times German hyperinflation, as Hawking puts it.
And the amazing thing is, the blueprint for all the structure we see today, galaxies, clusters of galaxies, seems to come from tiny quantum fluctuations, tiny ups and downs present during inflation. These fluctuations were stretched to enormous scales by inflation, and we actually see them imprinted on the cosmic microwave background radiation, that faint afterglow of the Big Bang. They're incredibly small variations, like 1 part in 100,000, observed by satellites like COBE and WMA. It's like the universe's initial quantum fuzziness provided the seeds for everything.
It's an incredible picture. As for the universe's ultimate fate, general relativity classically gives two main options. If there's enough matter and energy, gravity will eventually win, halting the expansion and causing everything to collapse back in a big crunch.
Hmm.
If there isn't enough matter, the expansion continues forever, leading to a big whimper, a cold, dark, empty universe as galaxies drift infinitely far apart. However, recent observations, especially of distant supernovae, strongly suggest that the expansion is actually accelerating again. This points back to that cosmological constant, or some form of dark energy or vacuum energy pushing things apart.
And the anthropic principle comes back here too, right? This vacuum energy has to be incredibly, almost unbelievably fine-tuned to be so nearly zero. Because if it were much larger, its repulsive force would have overwhelmed gravity very early on, preventing galaxies and stars from ever forming. So we wouldn't be here to wonder why it's so small. Our existence implies it must be small. And as you said, observations of supernovae, the cosmic microwave background, how galaxies are clustered, they all seem to converge on this picture of accelerating expansion, suggesting, as Hawking says, inflation may be a law of nature.
So it all comes back to Hamlet's nutshell. A tiny, slightly flattened imaginary time sphere, governed by the no-boundary proposal, somehow contains or encodes the entire history and structure of our vast, expanding real-time universe. It's a truly profound link between the quantum beginning and the cosmos we see today.
That's an incredible sweep, from the very beginning to the potential end. This profound shift in how we see the universe, its origins, its fundamental laws, naturally leads to that other ancient human quest. The desire to predict the future. People look to astrology, for example. Why is that so popular, yet scientists are generally so dismissive?
Well, astrology tends to make very vague forecasts. Personal relations may become intense, things that are hard to actually disprove. But the deeper reason scientists don't buy into it is that it's completely inconsistent with our well-tested theories, like Newton's laws or gravity or how forces work. There's just no known mechanism by which the position of, say, Mars could possibly affect the complex biochemistry happening inside someone here on Earth in the way astrologers claim. It doesn't fit with anything else we know about how the universe works.
Right. And the success of things like Newton's laws led to this idea of scientific determinism, championed by Laplace. The idea that if you could just know the precise position and velocity of every single particle in the universe at one moment, you could, in principle, calculate the entire past and future. But even classical physics runs into practical limits, doesn't it? Especially with chaos theory, the butterfly effect, where tiny, immeasurable differences in starting conditions can lead to massively different outcomes later on. Like trying to predict the weather accurately more than a few days ahead, it's practically impossible.
Exactly. Chaos puts a practical limit on prediction. And then quantum mechanics throws a fundamental spanner in the works of Laplace's perfect determinism. The uncertainty principle says you literally cannot know both the precise position and the precise velocity of a particle at the same time. The more accurately you measure one, the fuzzier the other becomes. So Laplace's starting condition, knowing everything precisely, is physically impossible. However, quantum mechanics brings back a different kind of determinism, a modified version. While we can't predict the exact outcome of a single quantum event, we can predict how the probabilities evolve over time. We can calculate something called the wave function for a particle or system. This wave function contains all the information about the probabilities of finding the particle in different states or locations.
Okay, so we can't know exactly where a particle is and where it's going simultaneously, but we can perfectly predict the odds. The wave function evolves predictably, according to the Schrödinger equation. And Hawking says, Even God is bound by the uncertainty principle. So there's still a kind of predictability, just a probabilistic one, but this all assumes that time flows smoothly everywhere, which brings us inevitably to black holes.
Exactly. Black holes really mess things up for simple determinism. The basic idea goes way back to John Michell in 1783, these hypothetical dark stars, so massive and dense that their gravity would be too strong for even light to escape. Later, Carl Schwarzschild found an exact solution to Einstein's general relativity equations in 1916 that described such an object, though its significance wasn't fully appreciated for decades. Even Einstein was skeptical they could actually form in reality.
And how do we even detect these things if nothing, not even light, can escape once it crosses the event horizon, that point of no return?
We detect them indirectly, by their immense gravitational influence on things we can see, like stars orbiting an unseen massive object at the center of our galaxy, or the behavior of matter swirling into them in systems called quasars, like NGC 4151. Now, classically, for an astronaut falling into a black hole, time would appear to just end at the singularity inside. While mathematically you can redefine time to avoid this absolute end, the real problem for determinism comes from Hawking's own revolutionary discovery. Black holes aren't completely black after all.
Ah, yes. The breakthrough Hawking radiation. The idea that black holes actually emit a faint thermal glow because of quantum effects near the event horizon. And this leads to a massive paradox for determinism, doesn't it? The information loss paradox.
It does. The basic idea involves those quantum fluctuations, again, virtual particle pairs popping in and out of existence. Near the event horizon, it's possible for one particle of a pair to fall into the black hole while the other escapes. To an outside observer, this escaping particle looks like radiation emitted by the black hole. It carries away energy. This means the black hole loses mass, shrinks, and over an incredibly long time, eventually evaporates completely. The paradox is, what happens to all the information about the stuff that fell into the black hole? When the black hole disappears, does that information just vanish from the universe? If information is truly lost, then we can't perfectly predict the future because we don't know what will come out of evaporating black holes, and we can't perfectly reconstruct the past because the information about what fell in is gone. It fundamentally undermines the modified determinism of quantum mechanics. Hawking even provocatively asks, maybe astrology is no worse at predicting the future than the laws of science.
Wow. That sounds like one of the biggest, deepest, most unresolved puzzles in fundamental physics right now. Is there any way out? Any hope for saving information?
It is absolutely one of the outstanding questions in theoretical physics today, as Hawking calls it. It's generated decades of intense debate. Many physicists are working hard on ways to show that information isn't actually lost, that it somehow gets encoded in the outgoing Hawking radiation, or maybe stored in some other way. One potential avenue mentioned in the book comes from the P-brane picture within M-theory. Perhaps black holes have microscopic structure related to P-branes, and the information gets stored as vibrations or waves on these branes, eventually reemerging as the black hole evaporates. Models proposed by Strominger and Vafa in 1996 hinted at this, but it's definitely still an active and very complex area of research.
Fascinating. And on a much lighter note, Hawking includes that great anecdote about his cameo on Star Trek, The Next Generation, playing poker with holographic versions of Newton, Einstein, and Data the android. He says he had a big surprise there and tells the reader to just look what appeared on my knee, which, if you look at the illustration of the book, is the book The Universe in a Nutshell itself. A fun little visual gag. Speaking of Star Trek, that brings us neatly to the question of time travel. You mentioned your friend and colleague Kip Thorne is famous for seriously investigating the physics of time travel, even though it's often seen as a bit, well, politically incorrect for physicists.
Indeed. Kip's work, often initially inspired by science fiction like Carl Sagan's novel Contact, really pushed the boundaries. It is a risky topic. You risk being dismissed as frivolous or, if you find something interesting, potentially facing unwanted military attention. But the serious scientific basis for even discussing time travel comes straight from Einstein's general theory of relativity. The theory allows for space-time to become so warped, so distorted, that pathways could potentially exist, allowing you to loop back and arrive before you started.
The classic science fiction trope is the wormhole, right? A tunnel through space-time connecting distant points or even different times. You can potentially use one as a shortcut across the galaxy, but if you manipulate the ends correctly, maybe travel back in time, which immediately raises the thorny issue of paradoxes, like the famous grandfather paradox. What if you go back and prevent your own birth?
Exactly. The grandfather paradox highlights the logical tangles. While those philosophical issues of free will are fascinating, Hawking, in the book, mostly sidesteps them. He focuses on the fundamental physics question. Do the laws of physics, as we understand them, actually permit the formation of these time loops or closed time-like curves, paths in space-time that return to their starting point in time?
So what does classical general relativity say? Are time loops possible in theory?
Initially, it seemed unlikely in realistic scenarios. But then, in 1949, the logician Kurt Gödel found a really shocking exact solution to Einstein's equations. It described a rotating universe, and built into its very fabric were time loops passing through every single point. You could, in principle, travel into your own past. Other theoretical possibilities emerged later, like one involving two cosmic strings moving past each other at nearly the speed of light.
Cosmic strings. These aren't the strings from string theory, right? They're hypothetical, incredibly thin but massive defects left over from the early universe, like wrinkles in spacetime. And if two whip past each other fast enough, they could warp spacetime enough to create these time loops. But okay, if these things are theoretically possible, why aren't we overrun with tourists from the future?
That's the big question. There's certainly no reliable evidence of future visitors, unless you believe in elaborate government cover-ups, as Hawking playfully suggests. But assuming time loops didn't just spontaneously form in the early universe, the really critical question becomes, could a sufficiently advanced civilization actually build a time machine? Could they manipulate space-time deliberately to create a localized region with time loops?
And Hawking came up with a crucial proof related to this, involving a very specific, very exotic requirement, didn't he? Something about negative energy.
Yes. He showed that creating a finite-sized time machine, one that wasn't there from the beginning of the universe, would necessarily require the presence of matter or energy with a negative energy density. Now, in classical physics, energy is always positive or zero, so classically, building a time machine is impossible. But quantum mechanics, as always, complicates things.
The quantum weirdness comes to the rescue.
Yeah.
Or maybe the opposite. Does quantum theory allow for this negative energy?
It does, at least locally and temporarily. Those vacuum fluctuations, the virtual particle pairs, can lead to regions where the energy density briefly dips below zero. And Hawking himself had realized that for black holes to evaporate via Hawking radiation, there must be a flow of negative energy into the black hole to balance the positive energy being radiated away. So the negative energy density required for time machines is allowed by quantum mechanics, at least in principle.
Okay, so quantum mechanics opens the door a crack.
Yeah.
But then it seems to slam it shut again with something called a bolt of radiation.
Precisely. This is the potential showstopper. If you manage to create a region where time travel into the past is just about to become possible, what's called a chronology horizon calculations suggest that virtual particles circulating just inside this horizon would get caught in reinforcing loops. They'd essentially travel around the loop infinitely many times in zero time, piling up and creating an infinite energy density right on the threshold. This would likely create a blindingly white bolt of energy and radiation that would destroy the would-be time machine and anyone trying to use it before the time loop could become stable.
So it's like the universe has a built-in safety mechanism. This led Hawking to propose his chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel by macroscopic objects. Is that the consensus now?
It's a strong conjecture, supported by that radiation argument, but it's not definitively proven in all possible scenarios. Interestingly, though, microscopic time travel is allowed, even required, by quantum mechanics. Feynman's sum over history's picture inherently includes paths where particles momentarily travel faster than light or even backward in time. These contribute to calculations. We even see tiny indirect experimental evidence for these effects, like small shifts in the energy levels of hydrogen atoms, the Lamb shift, and the Casimir effect we talked about earlier. So microscopic time travel is happening all around us. It's science fact.
But translating that microscopic weirdness into a macroscopic DeLorean is where the problem lies. The probability of forming the necessary macroscopic time loop seems practically zero. Hawking calculates the odds for Kip Thorne accidentally killing his grandfather via quantum time loop fluctuations as less than 1 in 10 with a trillion zeros after it. Pretty safe then. He jokes that Kip might just have a slight fuzziness around the edges, corresponding to that infinitesimal chance. And ends with a playful nudge. Perhaps this chapter is itself part of a government cover-up on time travel. You might be right. Okay, we've explored the universe from its quantum origins, the nature of time, prediction, paradoxes, even time travel. Let's shift gears now and look towards our own future. Star Trek paints this, well, quite comforting picture of a technologically advanced human society, but one that seems relatively stable, almost static, socially and biologically. Hawking really questions that vision in his book, doesn't he?
He does, quite strongly. He points to the current trends of exponential growth, human population doubling every 40 years or so, energy consumption climbing, the sheer volume of scientific output increasing exponentially. These trends simply cannot continue indefinitely on a finite planet. He calculates that if current rates persisted by the year 2600, the world's population would literally be standing shoulder to shoulder, and our energy use will make the Earth glow red hot. Clearly, something has to give.
That's a stark contrast to the USS Enterprise. And he also challenges the Star Trek idea of humans remaining biologically the same, just with better gadgets. He contrasts the incredibly slow pace of biological evolution via random DNA mutations, maybe one bit of information changing per year over millions of years, with the information revolution sparked by written language.
Exactly. He notes that a single paperback book contains far more information than the entire genetic difference between early apes and modern humans. Language allowed external information storage and transmission, massively accelerating the rate at which complexity could increase. And now we're on the verge of directly manipulating our own biology through genetic engineering. Hawking predicts that within 1,000 years, we'll likely have the ability to completely redesign human DNA. He believes this is almost inevitable, leading to improved humans, raising huge ethical debates, yes, but making Star Trek's vision of biologically unchanged humans seem unrealistic.
And then there's the potential for non-biological electronic life. Moore's Law, the observation that computer speed and complexity roughly double every 18 months or so.
Right. If that exponential trend continues, Hawking speculates that computers will eventually surpass human intelligence. His reasoning is quite direct. If complex chemical processes in our brains can lead to consciousness and intelligence, why couldn't equally complex electronic circuits do the same? He acknowledges the biological limits on human brains' skull size constrained by the birth canal, the relatively slow speed of chemical signals between neurons.
He says we can be quick-witted or very intelligent, but not both. Whereas electronic circuits, while having their own complexity speed trade-offs, operate with signals traveling near the speed of light. He suggests parallel processing, mimicking the brain's architecture, will be key for artificial intelligence to eventually overtake us.
So the future probably doesn't look like Star Trek's galaxy filled with slightly different humanoids. If humanity does spread to the stars, Hawking raises the Fermi paradox. If intelligent alien life is common out there, why haven't we seen any definitive evidence? Where is everybody? He offers a few possibilities. Maybe the emergence of life itself is incredibly rare. Or maybe the evolution of intelligence is rare. He even speculates whether intelligence actually confers long-term survival benefits. As he puts it, bacteria do very well without intelligence and will survive us if our so-called intelligence causes us to wipe ourselves out in a nuclear war.
Oof, a sobering thought. So the future, according to Hawking here, is likely one of rapid change, driven by biological and electronic evolution, vastly different from the stable galactic civilization of science fiction. We're likely on our own, but evolving fast.
That seems to be his conclusion. A future far more dynamic and perhaps unpredictable than often portrayed.
This leads us right to the cutting edge of theoretical physics, the ideas explored in the final chapter, the Brave New World. Do we live on a brain? Are we just holograms? Hawking introduces M-theory as this grand unifying picture, like a complex jigsaw puzzle. But he notes there seems to be a fundamental limit to how closely we can probe reality. The Planck length. He calls it the smallest Russian doll. What does that mean? Smallest possible distance.
The Planck length is an incredibly tiny scale, about 10^35 meters. It's the scale where quantum gravity effects are expected to become dominant. Our current theories, general relativity and quantum mechanics, basically break down there. Space-time itself is thought to dissolve into a chaotic quantum foam. To probe such scales directly with particle accelerators would require energies far beyond anything we can currently achieve machines the size of the solar system, potentially. But then comes this really exciting idea from M-theory. Maybe not all the extra dimensions it predicts, usually 6 or 7 beyond our familiar 3+1, are curled up super tiny at the Planck scale. Maybe some of them are actually much larger, comparatively speaking, or even infinite in extent. Like seeing a human hair from far away, it looks one-dimensional, but up close it has thickness.
And the crucial thing is this idea of large extra dimensions isn't just pure speculation. It's potentially testable. Future experiments, maybe at the Large Hadron Collider, LHC, or through extremely sensitive tests of gravity at short distances, could actually find evidence for them. or rule them out. This leads directly to the brain world scenario. What's the picture here?
The basic picture is that our entire observable universe, everything we know, all the particles and forces except possibly gravity, might be confined to a four-dimensional surface, or brain, embedded within a higher dimensional space, often called the bulk. So matter particles, light, electricity, the nuclear forces, they're all stuck on this brain. They can't leak out into the extra dimensions. This confinement could explain why we only perceive three spatial dimensions and why atoms are stable. Again, an anthropic connection. If electrons could escape into extra dimensions, atoms wouldn't hold together. Gravity, however, might be different. In some models, gravity can permeate the bulk, the extra dimensions.
And this could potentially solve that long-standing mystery. Why does gravity seem so incredibly weak compared to the other fundamental forces, like electromagnetism? The idea is that gravity is intrinsically strong, just like the other forces, but its influence gets diluted because it spreads out into these extra dimensions, making it appear feeble to us confined on our brain. And then there's the fascinating idea of a shadow brain existing parallel to ours, nearby in the bulk.
Right. If there was another brain close to ours, we wouldn't be able to see it directly because light would be stuck on that brain, just as ours is stuck on this one. But we would feel its gravitational pull. So matter on that shadow brain could act like the mysterious dark matter that astronomers observe through its gravitational effects, but which doesn't interact with light. It's an alternative explanation to things like WIMPs or axions. There's also another variation, the Randall-Sundrum model, where the extra dimension could be infinite but highly curved, like a saddle shape. This curvature itself could trap gravity near our brain without needing a second brain.
And that model has weird implications for black holes. Right. It wouldn't be spherical, but more like black pancakes spreading out along the brain. And they might radiate differently, emitting dark radiation gravitational waves escaping into the bulk dimension, which we couldn't detect directly. This could explain why we haven't seen expected signals, like gamma ray bursts, from certain types of dying black holes.
Exactly. These models make concrete, potentially testable predictions about how gravity might behave differently at very small scales, or how high-energy collisions might produce particles that seem to disappear into the extra dimensions. Going even further, Hawking uses the analogy of steam bubbles forming in boiling water to suggest that entire brain worlds might spontaneously pop into existence out of nothing due to quantum fluctuations in the bulk space-time.
So, connecting back to the no-boundary proposal, the imaginary time history of our own brain universe could be like a filled nutshell, a closed four-dimensional sphere that forms the boundary of a five-dimensional bubble existing in the higher dimensional bulk. And revisiting the holographic principle again. Are we living on the brain, the fundamental reality? Or are we just shadows, a holographic projection of what's happening in the higher dimensional bulk? Hawking, being a positivist, would likely say the question, which is real, is ill-posed. They're both mathematical models. The useful one is the one that best describes observations and makes successful predictions.
Precisely. And then you can speculate even further. What lies outside our bubble? Outside our brain? Maybe nothing. Maybe another identical bubble universe glued back to back with ours. Or maybe a whole landscape of different bubbles floating in the bulk, potentially colliding. Some have even speculated that our own Big Bang might have been triggered by such a brain collision.
It's mind-boggling stuff. But the key takeaway is that these seemingly wild, speculative models born from M-theory and the idea of extra dimensions actually offer concrete, testable predictions, especially about gravity at short distances, or phenomena at particle accelerators like the LHC, which, as Hawking notes with some regret, might have been explored sooner if the U.S. hadn't canceled the much larger superconducting supercollider, SSC, back in 1994. Wow. What an absolutely incredible journey we've taken through the universe in this deep dive. From Einstein's initial world-changing insights about relativity through the bizarre rules of quantum mechanics, the shape of time itself, the idea of multiple histories, the deep puzzles of prediction and black holes, the tantalizing possibility of time travel, the future of life, and finally these wild frontiers of M-theory and brain worlds. All guided by the profound thinking Stephen Hawking shared in The Universe in a Nutshell.
It really is astounding how far our understanding has progressed, driven by these theoretical frameworks and experimental tests, and yet how many deep mysteries still remain.
Absolutely. So we'll leave you with this final provocative thought to mull over. If our very existence as observers seems to filter the reality we perceive, as the anthropic principle suggests, and if all the information about our universe might, in some sense, be encoded holographically on a boundary surface, then is reality ultimately more about information than it is about matter or energy? And if that's the case, what completely new kind of nutshell might someday be needed to contain all of that information?